About the distance formula and its applications, we have to begin discussing about the section formula. Let's begin with discussing what is the section formula. Now, discussing about the section formula, what does it say? I am saying let P x1, y1, z1 and Q x2, y2, z2 be 2 points. So I am talking about points in space. Let P and Q be 2 points and R be a point. Now I don't know the coordinates of R. R be a point or either I should write R is a point where, first of all, R is a point lying on the line segment, joining P and Q, dividing that line segment joining P and Q internally in the ratio M1 is to M2. Then coordinates of R are, what are the coordinates? M1 x2 plus M2 x1 upon M1 plus M2. This is the x coordinate of R. M1 y2 plus M2 y1 upon M1 plus M2. This is the y coordinate of R. And M1 z2 plus M2 z1 upon M1 plus M2, this is the z coordinate of R. So this happens to be the coordinates of this point R, which divide a line segment joining PQ in the ratio M1 is to M2. What is the setup? Let us see. And also understand how do we get these as the coordinates of R. Say this is Z, this is X, and this is Y. And this is your origin, obviously. I have points P and Q in space with coordinates given to me. So suppose this is P and say this is, suppose over here there is somewhere Q. So this is my point P and this is my point Q. P has coordinates x1, y1, z1. Q has coordinates x2, y2, z2. Join the segment PQ. Consider this segment PQ by joining the points P and Q. It is given to me that there is a point R. There is a point R which is dividing PQ internally in the ratio M1 is to M2. So it is given to you that PR is to RQ is M1 is to M2. That is PR upon RQ is M1 upon M2. How to get the coordinates of R? The strategy is, what you do, just like we have adopted in the distance formula, drop perpendiculars from the point P to the xy plane from each of these points. So I am dropping perpendiculars from each of these points on the xy plane. Clearly they are going to lie on a straight line, all the foot of these perpendiculars. So I drew a perpendicular from the point P on the xy plane. It went on the xy plane and the foot of that perpendicular, suppose, is L. I also drew a perpendicular from R to the xy plane and the foot of that perpendicular, suppose, is R. Or R we have already taken. Let me take this as M. Also I drew a perpendicular from Q to the xy plane. This is the foot of that perpendicular, suppose it is N. Fine. Now what is the next step? Okay, we did this. Understand one thing carefully. What will be the coordinates of L, M and N? What will be the coordinates of L, M and N? I have already told you L is the foot of the perpendicular lying in the xy plane drawn from the point P. Right? So what will be its coordinates? x1, y1, 0. The x and the y coordinate remain the same, only the z coordinate becomes 0 because the corresponding point is lying in the xy plane. Similarly, M has coordinates what? So suppose I am saying this is x comma y comma z. Right now I don't know the coordinates of R. I am saying suppose they are x comma y comma z, then this is x comma y comma 0, and similarly this is x2 comma y2 comma 0. Now what you do? Drop a perpendicular from P to Rm and drop a perpendicular from R to Qn. So this is something very important step that is going to be coming over here, that is drop Pk. Let me say this is K and let me say this is S. So I am saying drop Pk perpendicular to Rm and Rs perpendicular to Qn. We drew this. So this is a perpendicular, Pk perpendicular to Rm and Rs perpendicular to Qn. Fine. Once we are through with this, just try to understand one logic. Again, I am revisiting the same concept. If P point is x1 comma y1 comma z1, how are these points obtained? How are these coordinates obtained? Length of the perpendicular drawn from P to the xy plane is equal to the z coordinate of P. Length of the perpendicular drawn from P to the xz plane is the y coordinate of P, and length of perpendicular drawn from P to the yz plane is the x coordinate of P. We have done that. So right now I am just asking you, this is a perpendicular which is drawn from P to the xy plane, so length of this perpendicular will be z1, that is the z coordinate. This is the perpendicular drawn from Q to the xy plane, so the length of this perpendicular clearly will be z2. This is z1, this is z2. Now I am asking you, what is Rk? What is Rk? For that, understand that what is this distance? What is Km? Now Km and PL are equal in length. You can see this figure, PL is equal to Km, PL is Z1, so Km is also Z1. Now this complete is Z2, right? What is this complete? From here to here. What is this? This is the length of the perpendicular drawn from R to the xy axis. So length of the perpendicular drawn from R to the xy axis is Z. That is the Z coordinate of R. So this complete is Z, this complete is Z1. So what is Rk? Rk is Rm minus Km. Rm is, what is Rm? Rm is Z minus Km is Z1. So Rk is Z minus Z1. Now that Rk is computed, let's also compute Qs. What is QS? QS is QN minus SN. Now QN you know is Z2. SN is what? SN is equal to RM. SN is equal to RM. You can see this. SN is equal to RM and this is equal to Z. Because it is nothing. What is RM? RM is the length of the perpendicular drawn from R to the XY plane, which is equal to the Z coordinate of R. That is small z. So Sn is equals to Rm is equal to Z. So you have Qn minus Sn and Sn is equal to Rm and that is equal to Z. So this is Z2 minus Z. Now I have got Rk, I have got Qs. Also understand PR is to RQ was M is to N, right? I've written this. PR is to RQ is M1 is to M2. And so, right now if you look at the figure, you can very easily see that these two triangles that you can see are similar triangles. This is right angles. These are corresponding angles and therefore AA similarity is adopted and you get these two right angled triangles to be similar. So here as PKR triangle is similar to triangle RSQ. As these two triangles are similar, therefore corresponding sides are proportional. What you get is PR upon RQ, PR upon RQ is equal to RK upon QS. What did I say? I am saying PR upon RQ is equal to RK upon QS is equal to PK upon RS. That's what is the meaning of sides, corresponding sides being proportional. Now that you have this, just use this portion of this equality. PR upon RQ. PR upon RQ. What is that? You know PR upon RQ is M1 upon M2. So you have got M1 upon M2 is equal to RK upon QS, right? RK upon QS. What is RK? RK is Z minus Z1 upon QS. QS is Z2 minus Z. From here you compute the Z coordinate of R, which is small z. Let's see, from here you have M1Z2 minus M1Z equals M2Z minus M2Z1. I've just cross multiplied. Now you can see you have M1Z2 plus M2Z1 equals M2Z plus M1Z. This implies M1Z2 plus M2Z1 equals M1 plus M2 comes out common times Z, and therefore you get Z is equal to M1Z2 plus M2Z1 upon M1 plus M2. And this actually is the Z coordinate of point R. So what you observed here is that when we considered perpendicular distances from these points to the XY plane, we actually got the Z coordinate. Similarly, when you are going to consider the perpendicular distance of these points from suppose XZ plane, in that case you are going to get the Y coordinate. So similarly, Y coordinate of R comes out to be M1 Y2 plus m2 y1 upon m1 plus m2. And similarly, when you consider the perpendiculars from these points, from collection of all reals minus singleton 0 to the collection of all reals like this function can be made continuous at x equals 0 by defining f of 0 as what? So basically, if you talk about f of x is given to you as 1 upon x minus 2 upon e to the power 2x minus 1. You can make this function continuous at 0 by defining f of 0 as what? F of 0 should be defined as limit x tends to 0 f of x. If this happens to be true, in that case I can say that the function f is continuous at x equals 0. But for this we need to first compute limit x tends to 0 f of x. What would this be? Limit x tends to 0 f of x is actually limit x tends to 0, this function. What is this? E to the power 2x minus 1 minus 2x whole upon x into e to the power 2x minus 1. Now you can just use the very expansion of this exponential function. What is it? E to the, or I should write 1 plus 2x plus 2x square by 2 factorial plus 2x cube by 3 factorial and so on minus 1 minus 2x as it is. I am just using the expansion of the exponential function, and then in the denominator as well this is 1 plus 2x square by 2 factorial plus and so on minus 1. 1 minus 1 gets cancelled, 1, 2x, minus 1, minus 2x, everything gets cancelled out. What you are left with is limit x tends to 0, this becomes what? 2x square by 2 factorial, then 2x cube by 3 factorial. So basically 2x square can be brought out common. You are left with 1 by 2 factorial and then rest of the terms have x term in them. How? This will be 2x cube by 3 factorial. So 2x square has been brought out, 2x is left by 3 factorial and then and so on. Fine? Whole upon, if you see carefully, this is 2x square, right? This is 2x into x, 2x square plus 2x whole square into x by 2 factorial and so on. So what I do in the denominator is I take out 2x square common. I am left with 1 plus. So from here 2x square has been brought out common. So you are left with 2x by 2 factorial and so on. Clear? You are left with 2x square has been brought out common. So 1, 2 is left, 1x is left and therefore 2x by 2 factorial is left. Rest all the terms are going to have at least one x term. Here also at least one x term will be there in all the next terms. So you can see 2x square gets cancelled. You are left with 2, 1 by 2 plus 2x by 3 factorial plus and so on whole upon 2x square is cancelled. You are left with 1 plus 2x by 2 factorial and so on. Now see, as limit x approaches 0, this complete thing becomes 0 plus 1, that is 1. So denominator is 1. This complete thing becomes 0, so you are left with 1 by 2 plus 0. So eventually what you get is 2 into 1 by 2 whole upon 1, which is 1, and therefore the limit that you get for fx as x approaches 0 is 1. F of 0 should be equal to 1 for f to be continuous at x equals 0, and therefore option number B is the correct one. Moving on to the next question, we have, if f is a function defined from collection of all reals to the collection of all reals like this, then compute the value of this limit. So what is the value of this limit? Let's see. It is limit x approaches to 2, fx minus f of 2 upon x minus 2. So my fx is this. If you simplify, see here x is approaching to 2, so I cannot take these values. F of 2 I need directly, I am going to plug in 1 over here. I am wanting limit x tends to 2 f of x. Now if you simplify this, what you get? You have x square minus 3x plus 2. right? And in the numerator you have x minus 2. Okay, so this becomes what? This is x square minus 2x minus x plus 2, right? So this becomes x minus 2 whole upon x, x minus 2 minus 1, x minus 2. So eventually you get x minus 2 upon x minus 2 into x minus 1. This is 1 upon x minus 1. Okay? So basically your f of x is 1 upon x minus 1. Now plug in place of over here. So this is 1 upon x minus 1 minus f of 2. F of 2 is 1 whole upon x minus 2. 1 upon x minus 1 minus 1 whole upon x minus 2. So what you get is 1 minus x minus 1, or I should write 1 minus x minus minus plus 1 whole upon x minus 1 into x minus 2. So this becomes what? This is 1 minus x plus 1. So this becomes 2 minus x whole upon x minus 1 into x minus 2. I can write this as minus of x minus 2, right? And so I'm left with minus 1 upon x minus 1. It is actually limit x approaches to 2. So as x approaches to 2, I get just minus 1 as my answer, and that is the required limit. Clear? Easy enough question. Next question is fx is sine x by x when x is non-zero. What do you think is going to make this function continuous at x equals 0? This function will be continuous at x equals 0 if f of 0 is defined to be equal to limit x tends to 0 f of x. So what is limit x tends to 0 f of x? This is pretty simple. Limit x tends to 0 sine x by x. You know that as x approaches to 0, when x is very close to 0, sine x, graph of sine x is almost same as that of the identity function. So sine x approximately becomes equal to x. So x upon x gives you 1, and this is how, this is the limit that is equal to 1. So limit x tends to 0, f of x is 1. You should actually define f of 0 to be 1 if you want that your function should become continuous at x equals 0. So for fx to be continuous at x equals 0, f of 0 should be defined as 1. Clear? Next question says if f of 2 is 4, f dash 2 is 1, what is the limit of this expression? Let's calculate. What is the limit of this expression? This is limit x approaches to x into f of 2 minus 2f of 2 plus 2f of 2 minus 2fx whole upon x minus 2. Clear? Now this becomes what? This is limit x approaches 2. You can take out f of 2 common from here. You're left with x minus 2 whole upon x minus 2 minus, let me write, plus limit x approaches to 2 minus 2 f of x minus f of 2 upon x minus 2. I'm just simplifying the expression, nothing else. So this gives me just f of 2. This is minus 2. Limit x tends to fx minus f of 2 upon x minus 2, which is what? F dash 2. F of 2 is given to me as 4. F dash 2 is given to me as 1. 4 minus 2 gives me 2. And therefore the answer of this expression is basically nothing but 2. Easy enough, just need to manipulate it accordingly so that you can use the very derivability definition as well. Now moving ahead, we are being asked the domain of the derivative of this function. So let's understand the function first. There are mod signs involved and therefore we need to open the very brackets up. So you have fx equals what? Let's see. So you have tan inverse x when mod x is less than equal to 1. Tan inverse x when mod x is less than equal to 1 means when x is lying between minus 1 and 1. Only then mod x is less than equal to 1. Then you have When mod x is greater than 1, that means x is strictly less than minus 1 or x is strictly greater than 1. When x is strictly less than minus 1, then mod x is negative, so mod x will be minus x. So this definition will be 1 by 2 minus x minus 1. Similarly, when x is greater than 1, that means x is positive, mod x is x, so you get 1 by 2 x minus 1. If you carefully observe individually in these ranges, these functions are continuous as well as differentiable, right? But the problem is at these points, minus 1 and 1. Let's check at these points the functions are continuous or differentiable or not. That is what is going to help us to define the very domain of the derivative of this function, right? So first of all, let me talk about x equals 1. Now limit x tends to 1 from the negative f of x. What is this? So from the left, x tends to 1 from the negative. It is tan inverse 1, which is pi by 4. And limit x tends to 1 from the positive. X tends to 1 from the positive is 0, which is not equal to pi by 4. That means f is discontinuous at x equals 1. Not continuous at a point implies not differentiable at that point. So function is not differentiable at x equals 1. Similarly, if I talk about the next interrupting point in the situation, which is minus 1, limit x tends to minus 1 from the negative. X tends to minus 1 from the negative. So x tends to minus 1 is going to make it 1 minus 1, 0. And limit x tends to minus 1 from the positive. Limit x tends to minus 1 from the positive is going to give you tan inverse minus 1, which is minus pi by 4, clearly not equal to 0. Again discontinuous at x equals minus 1 and hence not differentiable at x equals minus 1. So my function basically is continuous and differentiable at all the points on the real line except 1 and minus 1. So the domain of the derivative of the function will be r minus 1 and minus 1. Clear? So basically I am indirectly concluding the result because I am using the continuity scenario to get to the non-differentiability of the function at the 2 points. Now the next question says if alpha and beta are basically the discontinuity, points of discontinuity of f of x. Okay. Where fx is this, then a set of values of a for which the points alpha and beta and a comma a square are on the same side of this line is what? So first of all, what is f of x and what are the points of discontinuity for this function? F of x is given to you as 1 upon 1 minus x. Now this is not defined or not continuous for x equals 1, right? So f is discontinuous for x equals 1. So point of discontinuity of f is x equals 1. If I talk about f of x, is 1 upon 1 minus 1 upon 1 minus x. This is equal to what? 1 minus x whole upon 1 minus x minus 1. So this happens to be x minus 1 upon x, right? And then this is not defined for x equals 0 in the denominator, right? This was 1 minus x upon 1 minus x minus 1. So this is 1 minus x upon minus x or x minus 1 upon x. Then you have f of x is what? 1 upon 1 minus x minus 1 whole upon 1 minus x. So this gives you basically 1 minus 1 plus x